Sorry about that. I jumped ahead. So then we've got, so that was concentrated type forces. Then we've got these things called evenly distributed loads. Okay? So in this case, there's snow on that roof. And you know what happens if you don't design your materials that make up that roof. If you don't design them enough for the snow load, then you end up having a roof on the floor, don't you? Happened down a couple years ago down around the Nashville area, but it was ice, I think, mostly. And they had a situation where they lost a bunch of warehouse roofs. Happens. And then they show sandbags on a beam, so that's another type of evenly distributed load. Okay, so, and when they design these floors, that's what they design them for. And think in terms of, and you guys are so young, but there's a thing called a waterbed, right? You know, it's basically like a big old bladder that people sleep on. Well, if that is put on a floor, it's not as tough on the floor as just a conventional bed that's sitting on 4 posts, is it? Because you've spread the load out. It's evenly distributed. But if you take something similar in weight or even less, and you put that on 4 little pedestals, if you will, 4 legs, they could drive right down through the floor, couldn't they? Same thing with women in high heels. You know, the stilettos, they're tearing up the floor a lot worse than we are, because their weight is concentrated on that little bitty ball there on that heel. On the heels of our shoes, it's spread out, isn't it? So an evenly distributed load is a whole lot different situation on the overall picture. However, at the ends where it's connected, the floor, if you will here, where it's connected to the wall, it's really not going to matter, is it? Because you still have the same amount of weight acting on that beam. So you still have to account for that. If it's an evenly distributed load, what we do to that is we put it right square in the middle. If it's evenly distributed, it's right square in the middle of that beam, and it's all the way to that beam. Because that's a much worse case than when it was spread out. Does that make sense? So you always design to the worst case scenario, don't you? If it can handle all that weight right in the middle as a concentrated load, then it surely can handle all that weight as an evenly distributed load. That's what you're saying. Okay? So there's what happens to get the whole picture in there. So what we've got, and this is how you would see an evenly distributed load depicted on a picture on all these problems. It's all these arrows, and it says 60 pounds per foot. So all of this is 60 pounds. Every foot there's 60 pounds worth of weight on this. Okay? So to do our calculations, what we'll do then is the resultant force, that is 60, if you will, pounds per foot times 8 feet. So I think 60 times 8 is 480, right? If not, then the guy writing the book's wrong too, not just me. And the 2 feet cancel out, and you're left with pounds. So that's where that 480 pounds comes from. And then the distance from one side or the other is going to be 4 feet. Because I just got done telling you, you put it in the center, don't you? Okay, I wasn't lying. It's just what we do. So that force would be, that's what we'll study as opposed to that 60 pounds per foot over 8 feet. Again, because it's a much worse scenario. Okay? That's what he's telling you there on page 42. That's where that came from. Well. Oh, that's as far as I got. I didn't get any farther. Guess what? That's just about right, timing-wise, because we got about 2 or 3 minutes. Now, what I think I'll do, I've got some problems that I scanned in the other day. Let's